Alrighty, folks, so today we're talking about section 4.2, which, as I mentioned last time, is all about extrema, right? So in other words, maxes and minimums. So a number A is an absolute maximum on, of f on an interval I if the output of the function is bigger at A than at any other point on that interval. Right? And of course we have a similar definition for absolute minimum of f on I if the output of the function at A is less than the output anywhere else on the interval. Right? So one of the things to sort of batten down in your mind is that the output is what we're talking about being bigger or smaller. Right? Later on, we're going to come up with a list of potential maxes and mins, potential extrema, and we're going to talk about which one is biggest and smallest. And because we're talking about extrema, when we say that sort of thing, we mean the output is the biggest or the smallest. And so one of the nice things about these two is every continuous function has one of each if I is closed and bounded. Right. So in other words, it's you write it using square brackets, so it includes its endpoints, and it doesn't go off to infinity, right? So it looks like A, B, right, is how we'd write those sort of intervals. Another sort of thing that we deal with, another set of definitions we had in this section, is local maximum and minimum work similarly, but only nearby. Right, so not for all x in an interval. Right, or in any interval. So if I have a picture here, let's see, let me draw a nice smooth continuous. Right, so if we have this guy, let me redraw that because I need to make it more clear. Right. So this is the absolute maximum. This is the absolute minimum. This, 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 and this are all local maxes and mins. right? So it doesn't have to be the whole interval, but we have to be able to draw some small portion where it's either the smallest or the biggest, right? So it's not the smallest or the biggest overall, it's just locally nearby smallest or biggest. So let's see, more definitions. This was a section with a lot of definitions. So, you don't need there. C is a critical point if f prime of C equals 0 or f prime of C does not exist. Right, so we need to be careful to check out both of those. So the reason why that's important is that all local maxes and mins are also critical points. Right? And and absolute maximum mins are always local maximum mins or the endpoints. So the way this is going to work is we're going to find all the crit points, and we're going to find out which of those crit points are maxes or mins, or at least which of those crit points are absolute maxes or absolute mins. Whether or not they're local maxes or mins are going to have to wait till another section. But so the plan is to find crit points and then check for the biggest and smallest. So there's an intermediate step that I forgot. So let me move this down. So we're going to find the critical points, add in the two endpoints, and we're going to check all of those to figure out which one is the biggest and the smallest. And remember, that means in output, not of the four numbers. It's pretty easy to check which of four numbers is the biggest or smallest. One thing to note is that we don't get to go backwards, right? Otherwise, this step would be extraneous. Not every crit point is a maximum or a minimum. Some of them are something called inflection points, and some of them are just neither maxes nor mins. So when getting the crit points, right, we can't stop here because crit point is not the same thing as max or min, right? Crit point just gives us a small list to check and see whether they're maxes or mins, right? So we're always going to find the critical points, add in the two endpoints, and then check for the biggest or smallest, and this gets us absolute extrema. Right, so absolute maxes and absolute mins is how we get that. There's one more thing that was included in this section. We're not going to spend too much time on it because really it's just a special case of something that's going to come up in the next section. But it's included in this one, so I'll go ahead and throw it in here. Rolle's theorem says that if f of A equals f of B, and f is continuous on the closed interval AB, and f is differentiable on the open interval AB. So a lot of requirements here, but for most of the functions that we care about in this class, those are pretty simple. This is really the one you need to check. Then there is C in the interval from A to B with f prime of C equals 0. Right? And the basic idea there, right, is that f is continuous and differentiable, right, on this closed interval, which means that f achieves its maximum and its minimum. So I'm just going to go over the brief thing why. So f achieves a max and, so it should be an absolute max and an absolute min on the closed interval AB. Right? So if f of A equals f of B, then there are two possibilities. F of A equals f of B equals max and min, in which case f of x equals some constant and f prime of x is always 0. So you could pick any c that you wanted to and it would have to be 0. Or f of A equals f of B is the max or it's equal to the min, right? So it's one or the other. Then the other of those two is a critical point, right? Because all maximums and minimums either come from being endpoints, which we've just said it's one of these, so the other one can't be an endpoint, or maxes and mins come from critical points. So if it's a critical point, then f prime of C equals 0 or does not exist, but we said that f was differentiable, so that's not allowed, right? Because we know the derivative exists everywhere on that interval, so since we know there's a crit point, because one of the max or min is not an endpoint, then that crit point has to be f prime of C. This becomes a lot more useful with the mean value theorem, which lets us do all of this except we can throw away this part of it, which, like I said, is usually the one we have to check more diligently for, because we have some set categories of continuous and differentiable functions here in calculus, and we don't really have ways to move outside of that too much. But let's get some problems in finding extrema. Let's see. So right, so we're going to have some functions here, and we're going to talk about their finding their critical points in absolute extrema. So let's see. So we're going to do one quickly that we're going to talk through mostly and draw a picture. The rest of them we're going to do more calculus with. right? So if we look at this function, right, if this is 5, so this one's a little tricky to do unless you've had some practice looking at absolute value functions and the derivative. And I largely wanted to do this example not because we actually get to do a whole lot of calculus here. It's pretty easy where the local minimum is and where the local max is. But the reason why our process works here is because x equals 5 is a crit point. Right? And it's a crit point because y prime of 5 does not exist. Right? And so to see that, right, if we remember from our definition that the derivative is the limit of the slopes of the tangent lines, right? And like all limits, you have to consider the one-sided limits and see if they're equal, right? So if we take the limits from the left, right, we can clearly see that they're going to be the same as the slope of this leg of the absolute value function. So the limit of delta f over delta x as x approaches 5 from the left is clearly -1, right? Because that's what that straight line is when we're familiar with our absolute value questions. However, the limit as x approaches 5 on the right of delta f over delta x, right, that's going to be these secant lines, and those are going to match up exactly with the perfectly straight line that makes up that piece of the absolute value function. So that's going to be equal to 1. Right? So because these two limits are not equal, that's how we know that the derivative doesn't exist, because the limit as x approaches 5 in general does not exist if the one-sided limits are not equal. Right? So again, this is one where it's much easier to do if looking at the graph, right? It's pretty easy to tell what's the highest point and what's the lowest point. But we can get it this way if we're familiar with how the derivatives of absolute value functions go. Let's see. Next problem is going to be y equals ln of x divided by x on the interval from 1 to 3. So our first step in our process was finding the crit points. So that means we need to, so step 1, find the crit points, which means take the derivative and set equal to 0, and figure out where it doesn't exist. Right? So, take the derivative, right? We need to know y prime. This is a quotient. Clearly, it's dividing two things. So we want to get our low and our high. Right? Low is x, high is ln x. So it's low d high first. Low d high minus high d low. All right, so I should do this probably, just to make it clear where I'm getting all my stuff from. Low d high minus high d low over the square of low we go. We can simplify that to get 1 minus ln of x all over x squared. Right? So looking at this, we can look at this function and know that it does not exist if x equals 0, right? That's denominator problems, right? We can't let a denominator equal 0. And it doesn't exist if x is less than or equal to 0 because of ln. Right? The natural log, you can only plug in positive numbers into the natural log. You can't plug anything less than or equal to 0. However, these are not crit points. Because they are not in 1 to 3, right? Our entire problem, our focus is centered around numbers between 1 and 3, so the derivative doesn't exist there, but for this problem, those guys aren't critical points, which is good because that's an infinite number of critical points, and we don't really have the tools to deal with that. Right? So instead, we need to know when is y prime equal to 0. Right? So we've done this part. We need to do this part. Now, a function is equal to, or a fraction is equal to 0 when its numerator is equal to 0. So this boils down to 1 minus ln of x. So that's the same as 1 equals ln of x. And we know that you can translate this to the base of the logarithm raised to the power on the other side of the equal sign equals the input of the logarithm. So x equals e. Right? And e is between 1 and 3. So our critical points is just e. Right? So the first half of the question, which was to find the critical points, we're done. The critical points, really there's just one, so the plural doesn't need to be there, is just e. Right? So step 2 is to find extrema. Right? And that means we need to take y. We need to plug in the leftmost part of the interval. We need to plug in the rightmost part of the interval. And we need to plug in our critical points. Right? So this gets us ln of 1 over 1. So that is 0. This gets us ln of 3 over 3. And it's usually helpful to get an approximation of this. So let me find my approximation. This is about 0.3662. And y of e is ln of e divided by e. That's 1 divided by e, which is approximately 0.3678. Right? So now we look at these three numbers that we've gotten and we find the biggest and smallest. So the absolute minimum is 0 at x equals 1. The absolute maximum is 1 over e at x equals e, right? So when you're doing this, getting an approximation is usually necessary to figure out which one's bigger. Like, I couldn't tell you whether 1 over e is bigger than ln of 3 over 3. But when you're figuring out what those actual maxes and mins are, go ahead and put the exact value is probably good practices. Unless you're in a context where someone has told you that they want it rounded to a certain thing, right? Better to be exact when you can, right? So let's do one more. Let's do y equals 2 cosine theta minus root 3 theta on 0 to 2 pi. So again, to find the critical points, we need to take the derivative. So derivative of cosine is negative sine, and that constant multiple gets to just stick around. This is a linear term, so we just get to take the coefficient. Right? So there's no value that it's bad to plug into sine. Sine has the entire real line as a domain. So there's nowhere that it does not exist, right? Because the only theta that shows up is inside of sine, and sine can understand any theta. So what we need to do is take y prime and set it equal to 0. Right, so I can add root 3 to both sides. I can divide both sides by negative 2. And so now I need to figure out some solutions, right? And remember, one of the ways to go about that for a trig equation, once you have it looking like a trig function equals something, is, especially if it's sine or cosine, figure out a value, because there's no need to memorize all 16 when you can memorize 4, right? So we know, or we should know, that sine of pi over 3 equals positive root 3 over 2. And sine of theta is less than 0 in quadrant 3 and quadrant 4. Right? So if I want to get negative root 3 over 2, I need to use either the formula for reference angles that we have, or in the case of these really nice angles like pi over 3, I just have to pick the something over 3 that's in the right quadrant. Right? So 5 pi over 3 is the only whole number of pi's I can have over 3 and be in quadrant 3. Oh, sorry, that shouldn't be 5, that should be 4. Got ahead of myself. 4 pi over 3 is the only whole number of pi's I can have and be in quadrant 3. 5 pi over 3 is a solution, but it's the one that's in quadrant 4. Right? So we're using our powers of reference angles to come up with those two guys. So we know that there's an infinite number of solutions, right? The full solution thing to negative root 3 over 2 equals sine theta is theta equals 4 pi over 3 plus 2k pi and 5 pi over 3 plus 2k pi. Right? If we were just solving an equation, that would be the full list of solutions. But we have a restricted scope that we're looking at. So we just need to check, so our critical points are just 4 pi over 3 and 5 pi over 3, because if we add 2k pi to either of those, no matter what k is, then we're going to either get a number less than 0 or we're going to get a number more than 2 pi. So now we need to, so these are our critical points. That was step 1. Now we need to check y of 0, because that's the left-hand value here. This is going to be 2 times cosine of 0 minus root 3 times 0. So this is going to be 2 times 1 minus 0. So this is going to be 2. We need to plug in 2 pi, because that's the one up here. So this is going to be 2 times cosine of 2 pi minus root 3 times 2 pi. So that's again going to be 2 times 1 minus 2 pi root 3, which an approximation is handy. And we get a bunch of 8s going on there. Then we need to plug in our first critical point. And one of the nice things about these sorts of problems, and the way these trig functions play nicely with one another, if sine of something is related to root 3 over 2, then cosine is going to be 1/2, right? And since 4 pi over 3 is in quadrant 3, and cosine is negative there, I know this is going to be negative 1/2. And this is approximately negative 8.25 something. And y of 5 pi over 3 is not really going to have enough room, so I'm going to go ahead and take another line. This is our last problem, so there should be plenty of space. 5 pi over 3 is 2 times cosine of 5 pi over 3 minus root 3 times 5 pi over 3, which, again, anything where sine is related to root 3 over 2, and by related I mean either the positive or negative version of it, means that cosine is going to be either the positive or negative version of 1/2, and in quadrant 4, cosine is positive, so we get a positive 1/2 out of this. And that's going to be approximately equal to negative 8.06. So this is going to be our minimum, and this is going to be our maximum. Right? Our biggest and our smallest one. Right? So next up, we're going to sort of expand on that Rolle's theorem that we talked about last time. And we're going to learn some more tricks, some ways where we can figure out from these critical points which of these critical points are local maxes and local mins, right? We'll still have to plug in to figure out which ones are the absolute maxes and absolute mins, but it turns out we don't have to for local maxes and mins, and that's what we'll be talking about next time.